Of course, the vector valued functions we've been working with have position defined as a function of time t, but that is not the only way that we could define or parameterize our functions. We learned that in Calc 2 for beginners when we learned polar form, because polar coordinates are parameterizing with respect to an angle, theta, rather than time t. So if you have a point that's x comma y, you can get to that point a different way. We learned that x is equal to r cosine theta and y is equal to r sine theta. And then we also learned, we redefined r as a function of theta. So you'd say that's f of theta cosine theta, f of theta sine theta. So we learned all of this when we first learned polar form in Calc 2, right? So this is review. And honestly, it's to a certain extent a review of pre-calculus, because that's where the cosine sine thing is why x and y are defined as they are for a unit circle, right? So the cosine axis is the x-axis and the sine axis is the y-axis, and it's because of this parameterization. And of course, keep in mind that this would be rotating counterclockwise. Just having to do with how cosine and sine are defined. If you reverse them and put sine here and cosine here, it would make it rotate clockwise. Well, depending on what the function value is. All right, so we want to write the equation of the curve as a vectored valued function. So instead of r of t, we're going to rewrite it as r of theta. R of theta is equal to f of theta cosine theta, f of theta, it was supposed to be a parentheses and it did not work out, f of theta sine theta. There we have it. Okay, so now let's use the arc length formula to make this work. Arc length is the integral from a to b of the magnitude of r prime of, now we use t in the formula, but it technically could be any variable we want. So why not do theta? Just a modified. Right. All right, so, and actually because theta is an angle, we tend to use Greek letters for angles. So instead of A and B, we use alpha, which is the Greek letter A, and beta, which is the Greek letter B. That just tends to be how we make this work. Okay, so then that would be equal to alpha to beta, giant square root. It's going to be really big. Because the derivative of this, let me go find that real quick. R prime of theta would be equal to, you're going to need product rule to do this, right? Hello, product rule. Product rule, right, of derivatives. So you take negative f of theta sine theta, because the derivative of cosine is negative sine, plus f prime of theta cosine theta, and then f of theta cosine theta plus f prime of theta sine theta. You have to use the product rule for both of them, right? Because there are two functions multiplied. So the derivative of cosine is negative sine, leave the f alone, then take the derivative of the f function, leave the cosine alone, and then repeat with the sine function over here. So when I get down here, that's what I have to square. So that would be, I'm going to reverse this order just to make my life a little bit easier. It's f prime of theta cosine theta minus f of theta sine theta, all of that squared, plus, and then f of theta cosine theta plus f prime of theta sine theta, all of that squared. I take it back. My square root's a little too long. D theta. All right, so let's look at this again. Just to do a little bit of algebra real quick. I'm going to distribute this because, of course, this is a binomial times another squared. So if you take a binomial and you square it, you have to distribute it out. So let me write that one out. This is going to be so large, I'm not going to be able to fit this in. So let me do this one right here. Okay, so that would be f prime of theta squared. Right, so there's f prime of theta squared minus 2 f of theta, f prime of theta, sine theta, cosine theta. Oh, no, it's not 2. Sorry, it's just f of theta, f prime of theta. I don't know what I was doing there. Cosine theta. Because you're taking this one times that one twice. Oh, no, it is 2, right? Because you're taking minus f prime of theta, f of theta, and then another minus. So it is minus 2. There we go. And then plus, oh, fiddle faddle. Sorry, I forgot something. When I did f theta squared, I forgot about my cosine squared theta. There we go. Minus 2 f of theta, f prime of theta, cosine theta, sine theta. There we go. Because it's this term squared, and then 2 of the terms multiplied by each other. So sine of theta, cosine theta, f of theta, f prime. So that's this whole thing. So this is firsts, this is outers and inners, and then lasts, right, because I'm foiling, would be f of theta squared, and then sine squared theta. So all of that is just this guy squared. Now I have to still do the other one, and I'm running out of colors. All right, so I'm going to do this other one in purple right here. So that would be plus f of theta squared again, and then cosine squared. That's the part I forgot in the last one. Cosine squared theta, this is cosine times cosine, plus 2 f of theta, f prime of theta, cosine theta, sine theta, and then plus another f prime of theta squared, and then a sine squared. All of that is under the square root, and then it's all d theta. Oh my goodness. Well, yes, it's pretty horrendous, but there's some solutions. If you look at this bit right here and this bit right here, they're the same. So minus 2 of that plus 2 of that, it's all gone. And then I'm going to combine together some like terms. So the sine squared one and the cosine squared one. So let me put them together. This one right here and this one right here. So it'll be the integral from alpha to beta, big square root. It'll be f of theta squared, because they both have an f of theta squared, and then it'll be sine squared plus cosine squared. Well, here, maybe it'll be easier if I write it like this. Okay, so there's those two kind of light purple ones. This one and this one put together. They both have f of theta squared. And if you're noticing, hey, sine squared plus cosine squared, then indeed, that's going to make 1, which means this is going to be f of theta squared. Now, all of that is added to, now let's take these other two, this f prime one right here and this f prime one right here. So you'll notice they both have sine squared and cosine squared. So it's f prime of theta squared times cosine squared, and then plus f prime of theta again, and then it's sine squared. Oops, and we have to close that square root right here, and we have to slip a d theta at the end. Okay, but this right here, the sine squared and the cosine squared make 1, so this is just f of theta squared. And this right here, the sine squared and the cosine squared, again, make 1 by the Pythagorean identity. So that's just f prime of theta squared. Right? Because of the Pythagorean identity. So that means I'm taking my integral from alpha to beta square root f prime, or excuse me, f of theta squared plus f prime of theta squared d theta. So we just proved the polar equation form that I'm about to give you works. This right here is arc length in polar form. And that's where it comes from at the top of the next page. So at the top of the next page, hey, look at that polar form. Isn't that lovely? We just derived it. That's where it comes from. So we prove that that actually works. If you define your parameters x and y as we do in polar equation form right here, then we derived it, and that indeed is the arc length formula for polar form. Now to actually use that, I will see that in the next video.